Let's do a few examples trying to determine what molecule will have higher boiling point, for example, and we're going to be using intermolecular forces. And let's remember, London forces is the weakest, then we have dipole-dipole. Third, we're going to be considering if the molecule is capable of forming hydrogen bonds with molecules of the same type. Okay, now, let's see. I have a problem in, say that I'm being asked, what molecule, this is as isobutylene, but I'm being asked what do I think about which of these will have higher boiling point? That's acetone. Isobutylene and acetone. So now let's analyze in terms of intermolecular forces. So here what I have, that is the CH2, carbon, 4 bonds, we're good, CH3. CH3, I drew first the line structure. Now I'm going to be drawing all the atoms. So that's CH3, CH3. This molecule only has London dispersion force, somewhat branch out. So that's, the molecules cannot actually pile up efficiently. This molecule, the geometry, let's talk geometry, the molecule, just considering the carbons, the carbons are in the same plane. So, and now here also the oxygen, carbon, 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 all these atoms lie in the same plane. So not considering the hydrogens, the two molecules are trigonal planar. Say the geometry about the central carbon is trigonal planar. So you are having this and the atoms directly connected. So you have 3 atoms, and remember the carbon in the center has 3 bonding domains, 3 electron domains, which happen to be bonding. And because of that, applying Vesper, circumference, 3 domains, this is trigonal planar, angle is 120. All right. So, but now here, what's the difference? That in this molecule, you also have some London dispersion forces, but the strongest interaction is dipole-dipole. Here I have a vector showing that this one is polar. The extreme at the carbon is where the arrow starts, and that's delta positive, and that's delta negative. And so I can make like a little map, say that I have this kind of shape in my molecule, but this is delta negative and this is delta positive. Molecules can definitely arrange the way we're speaking in another video. They will be arranging according to those interactions. And to go from the liquid to the gas phase, separate these molecules takes more energy. So I expect that the boiling point of acetone is higher than the boiling point of the acetone, because here I have dipole, in addition to London dispersion forces. So, and let's see, the boiling point of isobutylene is minus 6.9 Celsius, so it is a gas. And the boiling point of acetone is, what is that? 56.3. So that's a liquid. So we can tell this interaction, because they're stronger, actually that's the state in which we will find acetone. This is much weaker. There's also a difference in melting point as well. But now, important that, again, the stronger intermolecular forces, you require more energy to produce the phase change. And give more heat to have more kinetic energy implies higher temperature. Okay, let's do one more thing here. Let's see that we're being asked to predict what molecule has higher boiling point. This, or 1, 2, 3, 4, this. Now, these are also constitutional isomers. Here I have 1, 2, 3, 4 carbon atoms. So this is the 4. And I have here 5 hydrogens, so 3 and 2 is 5. And 5 is 10 and 1 oxygen. You do the math. Here is the same molecular formula. Here you have 1, 2, 3, 4 carbons. Here hydrogens have 3 and 2 is 5, 7, 9, 10, and 1 oxygen. So same molecular formula. Therefore, these two molecules are constitutional isomers, meaning they share the same molecular formula, different connectivity. Atoms are arranged in different ways. Now, there's also a difference in functional group that you probably study in your organic chemistry. You will. This is an ether, and this is an alcohol. This molecule is diethyl ether. Diethyl ether, because this is 1, 2 carbons, an ethyl group. And this is 1, 2, 3, 4 carbons. So this alcohol is butanol. You can see that many cases as butanol, so norma is not ramified. Or you can also say 1-butanol. But if nothing is said, we understand this is the structure. All right, so now what do I have in terms of, if I'm being asked to predict which one will have a higher boiling point? Again, breaking interactions to go from liquid to gas phase. Now here, what type of interactions we need to be classifying here? So in this molecule, you always have London dispersion forces. There's some interaction between here, these bonds, but fleeting interactions. So London dispersion forces. But I also have dipole. Because I know that the bond between carbon and oxygen is polar, and there is a vector here. I can, if I translate those two vectors over, I know these will add up, and I will have a net dipole moment. So the molecule has a dipole. Now, let's see what are the intermolecular forces that are present in butanol. Again, you will have London dispersion forces. You have these fleeting dipoles in this part. You will also have dipole-dipole, because you have polar bonds, and that can arrange like this when we have polar bonds. So, for example, we have a vector that we can draw from the carbon to the oxygen. We can also, let's do this more explicitly. I can have the H here, and I will have another vector pointing towards the oxygen. So those two vectors translate. There is a permanent dipole. That's the situation. But also we have another interaction, which is hydrogen bonding. Remember that the way that you're going to recognize that is if you see hydrogens attached to either oxygen or hydrogens attached to nitrogen. That's the case here. So that's more polarized. So that's a stronger dipole-dipole interaction that we call hydrogen bonding. So in that interaction, you will draw this way. So here I have another molecule. 1, 2, 3, and 4 carbons, and you will have a network. We have a stronger interactions here. If we do have a stronger interactions, the mass is the same because they share the same molecular formula. There's no branching out. And because of intermolecular forces, here's a stronger interaction. I need more energy to break those molecules apart. So my prediction is that butanol will have a higher boiling point compared to the ethyl ether. The ethyl ether is around 40 some. I don't have that of the butanol with me. But we will continue doing problems now that we have all the concepts that we need about predicting trends in what is most interesting to us in organic chemistry. So mostly boiling point trends and solubility trends using intermolecular forces.